Okay, so I'm going to tell you a little bit about some of the pickup ions that we're seeing with Artemis. If you were here this morning, I described Artemis a little bit. It's a new two-probe mission with a full suite of plasma instrumentation around the moon. And the important thing that you need to know is that there's no mass composition instrument, but we do measure ions. They're just all smeared together, and we don't know what mass they are. Nonetheless, we can do something with this. So here's the basic idea. These ions are formed from the exosphere, from various species in the exosphere, and they feel the electric and magnetic fields in the solar wind. They're accelerated out laterally by the electric field, and at the same time they start to feel the force of the magnetic field, and they bend. The form of the trajectories that they follow is a function of the mass. The smaller mass ions have a smaller characteristic radius. The larger mass ions have a larger characteristic radius. And so you get both a spatial separation of these, and you also get a separation in terms of the angle that these are coming at you if you imagine flying a spacecraft through this plume. So that's the basic idea of what we're trying to do to recover from the unfortunate fact that we have no mass resolution. So here's this slide one more time, showing the various things that go on in the exosphere. I'm not going to get into this, but just to point out that a large proportion of these atoms that are bouncing around in the atmosphere being adsorbed and desorbed and recycled and so forth, eventually they get ionized by some process and they end up being picked up and carried off in the solar wind. A large fraction of them, in fact, in this way for all of these species. And that's where we see them with Artemis. Now, of course, the number of pickup ions that we're going to see from these things are going to be a function of a number of things. They're going to be a function of this distribution of these neutral atoms. They'll be a function of the density of those neutral atoms. And of course, they'll be a function of how efficiently those things are ionized, how well we get the ion output from this neutral input, as it were. So we have a lot to unfold. There's some previous observations that in some ways are better than us because they do have mass resolution. There's an observation from wind with a nice mass spectrum, which was actually very far downstream from the moon. There's an observation from Kaguya with a very nice mass spectrum that was very close to the moon. There's also some stuff from AMPT and even a little bit from Geotail out there. So Artemis kind of slots into a gap between these different classes. We're much closer than wind, but we're much further away than Kaguya, and it turns out that that's an efficacious kind of place to be if you don't happen to have a mass spectrometer. You can still get some separation of the ions. So without further ado, let's look at some Artemis observations. This is the position of the spacecraft. X is blue, Y is green, and red is Z. So you can see that we're at basically 0, X, and Y. We're out at the side. You can see that also in this orbit plot. Here are the orbits of the two probes. Here's where we saw a bunch of pickup ions almost straight out from the moon along the electric field, which is this red trace here. And here's what we see. This is the energy spectra, and the big red blob down here is the solar wind. These are the pickup ions up here, and here they are in angular space. So we're seeing this very narrow plume in both energy and angle, just this plume of ions coming right out of the spacecraft, right along the electric field and a little bit bent because they're starting to feel the magnetic field, but they haven't hit the peak of their cycloid yet. So how do you tell these guys apart? What are they? I'm doing better with the clicker than I did this morning. Here's the basic idea. So here are the two Artemis probes out here. Actually, the probes are right here. And here's the field of view of the bin that we see these ions in. And you can see that it's not all that narrow of a field of view. It's about 22 degrees across. But the width of that field of view constrains what species of ions can reach you there with the energy that you see them at. And in particular, for these two different cases, it does a more or less good or bad job of constraining the mass. For P2, there's actually a pretty big bundle of trajectories that can reach the spacecraft, encompassing a number of masses. For P1, we actually get a little bit more lucky because if you trace this bundle back, a whole bunch of them go below the surface of the moon. And of course, you can't get an ion from below the surface. So you really end up using the moon as kind of a virtual occulter of the ion trajectories. And so that's why when you look over here at the range of masses that could possibly correspond to this observation for this one particular time tick that I'm showing you, it's very broad for P2, but it's very narrow for P1. And so we see both of these kind of classes of things where we have kind of a decent constraint and kind of a terrible constraint, and it's everywhere in between. Here's where we see these things. We've got about 100 individual observations now. Here's the orbits in blue and green of the two probes. The orange points are times when the magnetic field is aligned in the right direction for you to see these things. So you need the magnetic field in the z direction so that the electric field points in the equator because the probes are in the equator. So to see them, you need E in the equator. The times when you see this and when you're sort of in the right angle to see a plume coming off are orange. The times where we actually see stuff is a subset of that, and it's these red points. You can see it follows these very kind of narrow plumes extending out from the moon. Here it is in another view where I've actually shown the velocity vectors of the ions corresponding to this, and I've put a couple of sample ion trajectories starting with various origins to kind of guide your eye and give you an idea of what these plumes match up to. And there's a pretty good spread in these velocity vectors, but in general, the distribution is clearly not corresponding to something low mass like helium or carbon or something like that. It's really more corresponding to something in this mass 20 to 40 range. If you do that more analytically, here's what the ions are allowed to be. So this is what you get from all the constraints on the energy and the angle of the ions that you're measuring, with no assumptions placed on where they can come from, actually. So we haven't put any assumptions on scale height or anything into this picture. All we're saying is that to reach the spacecraft in the energy angle bin where we see them, they could be this masses. In particular, 80% of the observations could be in this mass 20 to 40 bin. A much smaller percentage can be lower masses, and a smaller percentage can be higher masses than that. So this region is sort of favored. Of course, the real mass spectrum doesn't look like this. The real mass spectrum's got a bunch of little delta functions here, but this is just kind of the envelope of that. If you make some educated guesses, you can start to tentatively narrow this down, and that's what we've done here in this picture. What we've done here is we've assumed that you're much more likely to see ions that are coming from the surface or near the surface, because they're either sputtered off the surface or they're coming from low in the scale height of the ion. So if you guess that you're most likely to be looking at the ion that comes from nearest to the surface, then you arrive at a histogram that looks something like this. And this is little more than an educated guess at this point, so don't read too much into it, but it's got a couple of what I think you'll agree are very interesting peaks here at around mass 20 and mass 40. So let's see if my labels show up this time. So over here, here's all the kind of interesting ions that fall in this broad peak. Interesting things that we don't seem to be seeing very much of are helium and oxygen, so that's perhaps a bit of a surprise. And then when you go over to this much more processed spectrum, some of the things in these two peaks, for instance, in this lower peak, sodium and magnesium. Up here, potassium, calcium, argon's also close to here. And there are some other things in here. But if this is borne out, there may be some very interesting conclusions to reach from this. Right now, you should consider this very preliminary, and Menelaus is going to do a much better job and actually tell us what's going on here. So don't read too much into this, but it's at least suggestive and interesting, and there's more work to be done here. So if you do the same sort of thing, you also get a map of the source distributions. This is the raw occurrence. If you normalize that by the cylindrical volume element, assuming that they're sort of evenly distributed cylindrically, this is what you would get for the normalized kind of source production function, if you were. It has some interesting and plausible properties. They're all on the day side. They're concentrated towards the subsolar point, and there's some kind of a scale height story. So again, if all this stuff holds up, there's some interesting things to be said about the exosphere and its properties. You can try and correlate this to the driving parameters and see what's really ionizing these ions. So we tried correlating to solar wind flux. We also tried correlating to Lyman alpha flux. In the case of solar wind flux, you see a very good correlation. You can see I've got two sets of points here, and all I was doing was trying to see if there was some lag between solar wind input and ion output that made things match up better. And the answer is not much. The correlation function doesn't change much if you lag one or the other. So The solar wind seems to be driving a component of these pickup ions, and there doesn't seem to be much of a lag. So something to do with the solar wind, be it sputtering or charge exchange or electron impact exchange, is driving at least a percentage of these ions that we're seeing, which is perhaps no great surprise. On the other hand, Lyman alpha doesn't seem to do a whole lot. It also doesn't vary over a very wide range. So, from 4.2 to 5.0, should you really see a big correlation there because of increase in photoionization? It's probably debatable, but in any case, we don't see a big variation there. So this is kind of the state of things now. All of this was published in a paper about a month ago, and I'm happy to point people in that direction if they want more details. More hot off the presses until Menelaus comes up here with the hook and pulls me off the stage. Here are some new observations. Thank you. I think I should be perfect. Some new observations that I've just started looking at. So this is hot off the presses. I saw this picture in the summary plot, and I looked at it and I said, wow, there's more than one population of ions there in that energy spectrogram. And so I went in and I decided to dig into the velocity distributions and really see how many populations of pickup ions there are in this particular case. And lo and behold, there's at least 3. There's one here, one here, one here, and again over here. These guys are kind of smeared together. So I plotted some circles on here corresponding to where you should see various ions of different masses in velocity space for the solar wind conditions at the time. And you can see some interesting things here. Both of these blobs here are kind of in the mass 20 to 40 range, very much like what we've been seeing. There's another little blob down here that seems like it might be a lower mass ion, perhaps carbon or oxygen or something like that. The smear of these bins is big, so again, the resolution is not that good. But there's clearly multiple populations here, and they're clearly coming from different places because the energies are different. So on my last slide here, if you separate this mass spectrum into different angles, you find out that there's actually at least 3 populations of ions and probably more here. So these are both energy spectra, but they're for different angles. This top energy spectrum is for ions that are coming nearly perpendicular to the solar wind. So these are heavier ions that haven't been bent as much. This next one down here are things in the next angle bin over. These guys have been bent a little bit more. So they're either further along their gyro orbits or their lower mass, or a combination thereof. And this down here, you're starting to pick up the edge of the solar wind plasma. So that's not pickup ions. These are pickup ions. And you can see there's one population here. There's kind of a blob here that could be multiple populations. And there's actually 2 separate populations in energy in this angle bin. So I've got code running right now to try and analyze this, but right now I can't tell you much more than this stuff is higher mass, this stuff is lower mass, and it's coming from all across the swath of the moon from the subsolar point to the terminator. So if we can really unfold this, and if people like Menelaus can throw a really good model at it, we can actually tell you about things like solar zenith angle dependence, scale height, and hopefully mass fractionation. I think that's done. I showed this morning. When we have Laddie up there, of course, we'll have a lot more handle on this, and the 2 spacecraft, I think, are a terrific team to study this kind of processes. So thank you.